everyone. My topic is the dense image registration using sparse coding and bit propagation. Today I will review some introduction about the registration, and I will talk about the categories of the registration, and also I will talk about the SCoBeP. SCoBeP is the name of a registration method because this one is used sparse coding and bit propagation. I also review the backgrounds of the sparse coding and bit propagation method, and then I will talk about our proposed method, SCoBeP. In the SCoBeP, I will talk about how we can extracting the dense features, finding candidate points, and how we can just use the bit propagation in the SCoBeP method. And then I'll show you some experimental results for the registration using the SCoBeP, and also in the end of my presentation I will just talk about the conclusion and the future works. The registration is the process of the rendering two or more images of the same scene that they taken at the different times, or at the different viewpoints, or using the two different capturing modules or cameras. And also registration is widely used in the many applications like super resolution, medical image, change detection, and also remote sensing and so on. Okay. Here we can see that if we have a point or pixel in the fixed image grid, and if we just show this pixel as a point in the physical coordinates, and if this pixel now is as a point here, and we just transform it into another physical coordinates for the moving image, and we can see that all our physical coordinates of the fixed image, if we just assume that is here, and these two physical coordinates are they are not in the same position, so the point is here now is here for the moving image physical coordinates. So if you just show this point in the moving image, now we have the pixel here as a moving image grid. So this pixel in the fixed image, we cannot exactly just go through without any registration method. Go to the just in the another. We cannot show this pixel in the moving image grid without any registration method. Image registration methods have two different categories. One is the direct, and another is the feature-based matching. In the direct methods, the direct methods use all of the available image data, and the direct method is depend on the initialization points. That if the initialization points are close to the target points, we can just say that the results are so accurate. But in the feature-based matching method, this one just use the invariant features to ensure that ensure reliable matching, and this one is not dependent on any initialization point that are close to the target points. For the feature matching category, feature matching has the two categories like short baseline stereo matching and wide baseline stereo matching. In the short baseline stereo matching, we have two different viewpoints of the images. They can only differ slightly from each other, and they are not have a lot of differences. And for example, for in these two images, you can see that this one, there are not a lot of differences between this image and this image. So we can say that the matching became so easier, and we can, for example, at this point, this pixel here is appears at almost in the same position in the second image, but in the wide baseline stereo matching, we have the two images that they are significantly different viewpoints, and also they have some occluded areas. For example, for these two images, you can see that here has occluded. In this image, this one has this area has occluded by this sign. So we can exactly say that the matching problem in the wide baseline are so much more challenging than the short baseline matching. Okay. I just review the categories of the image registration. I said that as I said that the image registration has a two direct and feature-based matching. The feature-based matching will have the wide baseline stereo matching and short baseline stereo matching. In the wide baseline stereo matching, we have the dense and non-dense. In the dense, it means that we just used our registration method for each pixel of the image, but the non-dense doesn't matter, and we don't use the exactly. We don't use the registration method for each pixel of the test image, and our SCoBeP or our registration method is here. And you can see that our SCoBeP is the dense, wide baseline, and the feature-based matching registration. SCoBeP has 4 main steps. The first one is the exacting the dense features. The second one is the finding candidate points. The third one is the applying bit propagation. And the last one is the mapping or synthesizing the reference image into the test image. It means that we use the pixels of the reference image and just displaying the test image by the reference image pixels. And we can say that these two steps are the most important of our registration part, and also feature extraction and matching are most dependent on the image characteristics. Okay. In this here is the, you can just plot the SCoBeP method using our SCoBeP method. Okay. If just assume that we have the reference image and the test image, and this, for example, these two pictures that you can see that both of them are the wide baseline images, and we just for the both of them just extracting the features, and the features can be the blocks or the SIFT, and also in the next step we just constructing the dictionary from the features that just extracting from the reference image, and in the next step just try to find the candidate points via the sparse coding, and using the dictionary and the extracted feature from the test image. And the last step is using the bit propagation for finding removing the bad candidate points and just finding the good candidate points. And the last step here is the output as a warping the reference image to the test image. For the extracting the dense features, we can say, for example, because our SCoBeP is the dense for each pixel in the image, we just found the block, or now we call it the features as a block, and you can just assume that instead of the block features, you can have the SIFT features. Now I'm trying to just explain the block features. For example, for each pixel in this image, we have the block, and then after extracting the block, we have the block here, and just vectorizing the block to the one vector. So if we have we just call the reference image as x and the test image as a y. To extract these features, we have the patch of the size of the S as the size of the 2k plus 1 squared, that this one is containing the neighborhood of the neighboring pixels around each pixel on both images of the test and the reference image. So we can say that the Yij, just define the Yij as a feature vector of the vectors patch of the Pij in the test image, and then we just construct the 3D test feature image of the Y, that each coefficient of this one is one of these feature vectors. So this Y has a 3D and has the M, N, and because this one has the size of the S, so this one has M, N, S. The next step is making a dictionary from the reference image, and so we just define the D as an S, M, N, that these reconstructed with all possible vectors of the Xij as a D columns vector, and Xij is the same as we just have the same as the Yij here, but instead of using the test image pixels, just using the reference image pixels. So after defining the Xij, we just create the D in this format, and you can see that our D is the fat matrix. Yeah, it's meant that, for example, the number of the row is more or less than the number. Yeah. Oops. Yes, it's less than of the number of columns. Okay. Now is the time to just say a little about explain a little about the background of the sparse coding. The sparse coding models data vectors as a sparse linear combination of the basis columns, and the data is described as a combination of the columns vector features that involves both additive or subtractive interactions. And for example, if just consider that we have the Y as a signal and the fat matrix of the D, and we are interested in presenting Y with the column of the S space of D, and we try to finding the alpha such that the Y is equal to D alpha, and alpha is a sparse. Yeah, and the sparse is means that the most of the coefficients of the alpha are 0. And we can just write down as a mathematically the problem of the sparse coding like this, as try to finding the alpha. And in our sparse and in our SCoBeP registration, we use the subspace pursuit algorithm for finding the alpha as a coefficient. Okay, just back to our SCoBeP registration. Now we just found we just make the dictionary, and also just have the features of the test image. So now we are trying to find the candidate points via sparse coding. The goal of this step is to find the candidates of the Xij that they are so similar to the input of the Xij in the test image, and we try to solve this sparse coding problem using the, for example, subset pursuit or OMP, and we try to finding the alpha ij. We can see that we have the D as a dictionary here, and we have this one has the one of our feature vectors, and we try to find the sparse coefficient vector of the alpha ij. Here we just found the alpha ij using the sparse coding. Now we have the alpha ij, and we try to pick up the n largest coefficient of the alpha ij as our n candidates for the next step. So you can see that, for example, if this one is our test image, this one is a reference image, we can say that this one as our block here, we just find five candidate points that are similar to this one. And you can just be sure that if you remember, I said that the sparse coding is the linear combination of the basis columns, and that one is mean that you can see that, for example, this one is not similar to this block, but as the definition of the sparse coding, all of these five candidate points, they can make this block in the test image. Yeah, for example, just this one or this one or this one, they are not exactly this block in the test image. Okay, and now is the time for the think about the just a little briefly just talk about the BF propagation. BF propagation, as all of you know that is an approximate inference method that uses graphical models, something like such as factor graphs, and the BP or BF propagation performed by the passing messages through the factor graph of a given problem. A factor graph is a graph that contains two types of the nodes, and the variable node and the factor node. The variable nodes are assigned to the variables, and the factor nodes show the relationship between the variables. And in our problem, we have the factor node here that we just put it as a prior, and this one is those five candidate points. The goal of applying the BF propagation in our SCoBeP is just finding the best match point for the test data, using those candidate points from the reference image that just uses them as a prior knowledge. In our case, we assign one variable node for each pixel in the test image, and also connect each pair of the neighboring pixels with a factor node, and also we have the one extra factor node, and you can just see here as a gray slide, and we have the one extra factor node to take care of the prior knowledge that obtained from the candidate points. We just found the candidate points in the sparse coding step. Applying BP on applying BP on factor graph of test image. We just applied the BP on factor graph of the test image. That we have the n candidate points as a prior knowledge, and when BP is running, it can change the probability of the candidate points based on the probabilities of the neighbors. And for example, if I can just for the applying the BF propagation, if Ni is the variable node I, and Na is the factor node A, and Mi to A is the forward message from the node I to node A, and also the MA to I is the backward message from the node I to node A, and also MA to I XI is the belief of the node A, and that shows that how probable that the pixel of node I in the test image can map to location of the XI in the reference image. So in the first equation for finding the MIA, this one is for the updating the MIA for all of the variable nodes and factor nodes. For the MIA, you can just use this equation that the NI, this one, this definition is means that the neighbor of the node A, and that excluding the node I, and for finding the MAI XI, just use this equation, and the factor node A is between variable nodes I and J. And the function fxi xj for this one just defined as this equation, and the sigma square is the parameter to control the relative extent of the geometric concentrating by a neighboring node. And yeah, this one is mean that the far nodes has less effect on this and yeah, in this message. Okay. Okay. The end of the belief propagation method, we have we just remove the bad candidate points, and we have the best candidate points for each pixel, and then we can just select and divert the reference image to the test image. And now I want to show, after this one, I want to show some experimental results and some pictures. Okay, for the data set of our experimental result, we just use all of them are the wide baseline images with different scales, contrast, and rotated scenes and deformed objects. And we have for each of them and the mix of all of them, we have some experiments. And also the tested images were taken in the normal indoor or outdoor setting, and the resolution of each of them is 200 by 200 pixels. The parameters that we used in our SCoBeP, we can have the n or number of the candidate points that we just use 5, and the patch size of for the extracting features, the K was 3, so that one has the 7 by 7. For the part of our feature extraction, we use the block and SIFT, as I said, and also for the next step for the Sparse coding for finding the candidate points, we just try 3 methods, OMP and NCC as a normalized cross correlation, and also SIFT. And you can see that, for example, this one is as a reference image with the test image, and we use the block and OMP here, block and subspace persuade here. And in our results, using the block and the subspace persuade was the best quality and best PSNR. In this slide, I want to show you comparison among the SCoBeP, Optical flow, and SIFT-flow. And the over images that they have, the contrast changes. And also the numbers under the columns, under each image is the PSNR. So, and the red circles here just try to highlight the weaknesses or the strength of our proposed method, and also for the weaknesses of the SIFT-flow, the optical flow, and SIFT-flow. For example, here you're going to see that for this mode, if this one is a reference image and this one is a test image. For this one is the synthesized image synthesized the image using our SCoBeP. Yeah, it means that we just try to using the reference image pixels to mapping and to showing the test image. So this one should be similar to the test image. But for example, here you can just see the mark, the body of the marks here, but don't have the mark in the test image. And here has you just have the comparison over images with the escape changes, and you can see this one is for the optical. For all of the results, the second one is for this. The second one is SCoBeP. The third one is the optical flow, and the last one is the SIFT-flow. And you can see also the PSNR, the under of each images. And also for this one we have the escape changes. And here we can see that the rotation changes. And this one is the deformation. And here, because we have a lot of experiment, we have a lot of we just have a lot of experimental results, and just try to show put the PSNRs for each of them, and also the average of the PSNR for the SCoBeP, SIFT-flow, and optical flow. And also here, I just try to plot the SCoBeP, SIFT-flow, and optical flow, and you can see, and also this one as a average, the SCoBeP average, and SIFT-flow average, and the optical flow result average for each method. And finally, the conclusion. I just try to briefly just talk about the SCoBeP. That the SCoBeP is the dense image registration method for using for the wide baseline images, and the techniques that use the Sparse coding, and also using the propagation method. And we can use the SCoBeP on many applications like super resolution 3D medical image registration, remote sensing, and so on. And any question?